2021 coverage of TCT 360 is sponsored by E3D. Their new Rapid Change Revo combines a toolless nozzle swap, all-in-one ceramic heater core, and Revo Micro Cold End to give your printer a lighter, safer, quick change hot end system. Check the link in the description to find out more. Hello everyone, Adam here again at TCT Show 2021. So here at Slice Engineering with Dan. Dan, welcome back to the UK. I'm guessing you've been here before.
I have briefly, actually. So this is only my second ever trip to the UK, so I'm super excited to be here, actually.
Excellent. I am too, having been stuck in the house for 18 months. So first, can you let us know what it is you do at Slice Engineering as a company, and also personally what you do there?
Sure. So at Slice Engineering, we make hot ends and other 3D printing components for specifically FDM machines. So we don't do anything with SLA or SLS or anything like that, but anything having to do with FDM, we can help with improving performance, speed, reliability, things like that.
So for those that are not familiar with any of your products at all already, can you name a few that they may have heard of?
So the Mosquito or Copperhead are probably the things that you may have heard of, especially if people are watching your channel. They've probably heard of the Mosquito or the Copperhead. Those are our main hot-end product lines that focus on sort of the prosumer and industrial market or the hobby market, depending on what your application is.
Okay, sounds good. Yeah, definitely the Mosquito probably should be heard of. So what's kind of the latest trend with what you're doing? What's your latest products that you can talk to us about in terms of performance and like high-speed printing?
Sure. So we just recently launched our Magnum Plus hot end, which is in the Mosquito product line. So it's still a Mosquito, got the same features as a regular Mosquito, but it also has the opportunity to print at much higher speeds. So a normal hot end will do 15 to 20 cubic millimeters per second of flow rate. This one does up to 80 to 90 cubic millimeters per second. Of course, depending on your setup, what material you're printing with and things like that. But the intent is really high throughput without sacrificing a lot on the resolution side. So people are still printing sometimes with a 0.4 nozzle and getting phenomenal resolution prints like what you would expect from a Mosquito. But then you're able to swap to a different nozzle pretty easily with our one-handed nozzle change and print something at really high flow rates. So that's basically what we're talking about today.
So you mentioned there a little bit about how you're printing at much higher flow rates. How do you go about achieving that? Because obviously you can't just force plastic harder, especially, the hot end is not doing any of that forcing. So what kind of parameters are you adjusting in order to increase that flow rate to such a high speed?
Sure. It's a great question. So one of the things that we found when we were experimenting with trying to push the limits of what can be done with high flow printing was that, as you increase speeds, little details matter more and more. So one of the little details that matters a lot actually is nozzle threads. So threads, even if you've got a really well-machined thread, you've still got this sort of, show this to the camera here, this sort of air gap between the male and female feature. And that air gap actually makes a difference. You've got an insulator there. Air is acting as an insulator. And then also, as those features interact with one another, the main form of heat transfer there is going to be conduction. So you've got very little, comparatively, physical contact between the threads in the nozzle and the hot block. So you're not conducting that much heat really to the nozzle. So what we've done is our Magnum Plus uses shorter, same length nozzles as everything else, 12.5 millimeters. And so that, by eliminating that, we've got the plastic coming directly into contact with the hot block. So you've got, conduction all the way through the melt zone, as opposed to going from the hot block to the nozzle with all this thread space where you're getting really poor conduction across that surface.
So it sounds like essentially if we look at it from kind of a flow diagram point of view, you're taking out one of those steps, so that loss of efficiency just disappears from the equation completely, and you're going straight from the hot block, which is obviously hot, straight into the material.
Exactly, yeah. So we're directly heating instead of putting a barrier in the heating process, and that really helps to achieve higher flow in a pretty small, compact package.
Does that allow you some additional freedom in what you do with the nozzle in terms of material and things as well, because you're a little bit less reliant on it for your flow rate capabilities?
Yeah, so we have a couple of different nozzles, and sort of putting a smaller nozzle on it, like I mentioned, gives us that better flow rate capacity, but also gives us a lot of flexibility in terms of what nozzles we can put on the hot end. And we've got our Bridgemaster and vanadium nozzles. Bridgemaster is a copper substrate with carbide coating, and those are really, really good for conducting heat to the filament as well, because again, you've got copper on copper essentially. So that gives you a better output in terms of maintaining the filament temperature as it's exiting the nozzle than pretty much anything else that's available. So it's that's sort of thing about nozzles.
So thinking more about the peak flow rates and maybe a versatility in the overall design, what kind of range of power do you have to put into this heat block in order to get that high flow rates, or something maybe more day to day?
Sure. So we've got like 70-ish different options for how you can configure Magnum Plus. So if you wanted to not go full bore, there's an option for you as well. So we start at 50 watts of heating power and we go up to 100 watts of heating power. We'll handle 12 or 24 volt, although I'd recommend with that much power you should probably be running a 24 volt system. So please change to 24 volt. And then it will take up to 2 temperature sensors as well for redundancy. Again, when you've got this high power system, you're putting out a lot of plastic, and 100 watts is a lot of power in a little tiny package. And the capability of melting something or causing damage somewhere is higher. So having a redundant temperature sensor, I think, is a helpful thing. Again, optional, but is available, especially if you've got a sort of a mission critical application.
Yeah, I mean, with a lot of talk, rightly so, about safety in 3D printing, it's really good to see you have some levels of redundancy that others are not looking into, especially when you're living life on the edge with the extremely high power and flow rates that you can expect.
Yeah, absolutely. I mean, we're definitely all about safety. We run these in our own lab, in our own office. So we are very interested personally, in ensuring our own team's safety and our safety, and so we care a lot about that. We care a lot about putting out a safe product that's going to work well.
So with the capability to print like really fast, super high flow rates, you're obviously going to be able to print really big things comparatively quickly. And as you're printing from time to time, obviously material dependent as well, you can get plastic buildup on the nozzle, and then it can drop off onto your print and cause disruption or failure or all sorts. Apparently, you've got something that can potentially solve this problem.
Yeah, we do. So we have a product called Plastic Repellant Paint. It's basically just what it sounds like. We try to, be as relatively straightforward as we can with naming some of these things. So it's a paint that it comes in a little tiny vial, and it's an aqueous nano suspension of PTFE particles. So what that means is it's water, mostly water. It's like 98% water, and in there are little tiny particles of long chain PTFE, which most people will know as Teflon. And what that allows you to do is you open it up. There's a little brush on it. You just brush it on your nozzle. It's dry in 30 seconds, and it changes the surface energy of your nozzle or your hot block. And so when you're, especially on the long print where you've got maybe your bed's not perfectly level or whatever, you're essentially like running into the print constantly, you have problems with plastic adhesion that can cause, like you said, massive failures, which could be super expensive or just super annoying. You don't want to ever wake up to a hairy ball messed up plastic.
Everybody hates the spaghetti monster.
Everybody hates it. So this can help with that, help reduce that. And it's super easy to apply, like I said, in 30 seconds.
Are there any limitations in terms of temperatures that you can print with, or nozzle materials that you have to kind of consider when using something like this?
Not nozzle materials. It will literally apply to anything. You can apply it to plastic or metallic surfaces. But there is a temperature limitation. We rate it to 290 degrees Celsius. And then after that, basically it starts to, it just starts to deteriorate. So if you put it on your nozzle, heated it, to 350 or something, it's just going to not be effective anymore. And so you would have to reapply a new coating, which again takes 30 seconds. So it's not a difficult thing to do, but it's not going to be as plastic repellent beyond 290 degrees Celsius.
And it sounds like with covering 290 degrees, you've got most of the like consumer range plastics. You're going to be looking at printing anyway. You've got to be pretty exotic to get above 290 with your printing temperatures, right?
Yeah, the people that are going above 290 consistently probably need a slightly different solution. But this is great for your PLAs, your PETGs, even your nylons, depending on what grade you're printing. So it'll cover the vast majority of the things that people normally would be printing with on an FDM machine. That's not like fully enclosed, and
and as far as I'm aware, there's another thing that we can put on the end of our hot ends that you've just produced recently. Can you tell us about that one?
So people have been asking us for a silicone boot, or a sock. People call it a sock, for a very, very long time. We finally came out with one. The delay was due to the fact that we were trying to make it in the US, and it's very difficult to find a silicone molder in the US. So anyway, we have a sock now, but we call it a boot because it's a little more rigid. It is designed to sort of wrap around and grip onto the hot block so that it doesn't, as you heat up the hot block, as you heat up the hot end, it's not going to sort of slouch and fall off. It also grips onto the nozzle, so it kind of it grips in two places. It grips on really well, so it doesn't fall off, because that's annoying too, and can also ruin a print. So yeah, we have that boot. It's also rated to 290 degrees Celsius. I think we might say 300 on the website, but anyway, it's 300. So it's not a super high temperature rated, so you can't put it in an enclosed chamber and print peak with it on, but you can print, again, all the other filaments we just talked about, your ASAs, your nylons, all those things can be printed with this boot on there. And it's also coated with a formulation similar to the plastic repellent paint that decreases plastic adhesion, which is a nice thing. And it's flame retardant.
Okay, well, Dan, thank you very much for your time today. It's been great to meet you finally, having talked over the internet a little bit. Yeah, it's quite a special occasion, isn't it? So, hope you enjoy the rest of the show, and thank you very much. Cheers.
All right. Good. Awesome.